this is a good place to be, right?
Yeah.
We're working no major issues right now. Everything looks nominal, and let's just, fingers crossed that we stay that way.
Our T0 currently locked in at 7:30 and 50 seconds a.m. We do have a 20-second window, but no more, because now we've locked in that T0.
Correct.
So we have to hit it at that second, or we're not flying today.
Correct. And I want to, tip my hat off to both the LSP flight design teams who worked tirelessly here to extend that launch window to the 20 seconds that we do have. Meaning that if we do run into an issue, we have some time to kind of clear that issue to hopefully get off the ground today, which we are going to do. We're going to launch today. I'm pretty confident.
And a real quick note on the NLM poll where Dr. Denton Gibson gave a shout out to a gentleman who's retiring after 40 years.
Yeah, I want to just also give a shout out to Mike Carney as well. I started here in LSP in his group, so I have some fond memories of Mike Carney. So I just want to say Godspeed as he goes into his next chapter of his life. He will be missed.
All right, we'll be tracking in the meantime all of the action as it happens and unfolds. We've got the IMAP to internal power coming up at T-minus 15 minutes. And for now, we'll send it back to the host desk.
Thank you, guys. All right, now let's learn more about the National Oceanic and Atmospheric Administration's, or NOAA's, newest satellite. SWIFO L1 is roughly the size of a washer and dryer, while its solar panel is about the size of a door. When fully fueled, it weighs about the same as a large grand piano. It is the first NOAA satellite designed specifically to monitor space weather 24/7, serving as an early warning beacon for potentially disruptive events.
Meet SWIFO L1, NOAA's first purpose-built space weather observatory. When a solar storm erupts from the sun, SWIFO L1's coronagraph observes the event right away and sends the data back to the SWIFO ground segment, a network of antenna stations all over the world, with the SWIFO command and control in Maryland. But spotting a storm is one thing. Actually measuring it close up is another. It's the difference between tracking a growing hurricane on radar and flying through the storm on a Hurricane Hunter aircraft. SWIFO L1 does both. After the spacecraft spots a storm with its coronagraph, it watches the approaching weather and waits. Somewhere between 18 and 70 hours later, the incoming storm passes over SWIFO L1. Then, the spacecraft's instrument suite measures the storm's severity and speed and sends that data home too, giving NOAA early warning somewhere between 15 and 60 minutes before the storm arrives at Earth. NOAA's Space Weather Prediction Center in Colorado is constantly on the alert, using all the data SWIFO L1 collects to develop and communicate real-time forecasts and warnings to industry, government agencies, and the public, so they can take action before the storm arrives to minimize its impact.
Now, you heard about NOAA's Space Weather Prediction Center in that video. Here's NASA's Joy Ung live at a nearby viewing location with that center's director, Clinton Wallace.
Clinton, thank you so much for joining us today.
Good morning. Yeah, beautiful day for lunch.
Yes. Are you excited?
Very excited. So I can't wait.
So the Space Weather Prediction Center at NOAA monitors space weather 24 hours a day. Can you tell me who relies on that information?
Well, Joy, today we're more vulnerable than we've ever been to space weather because of the technology that we rely on and the advancements that we've had. So everything from power grids to people using GPS to aviation, even our astronauts rely on space weather information.
And can you tell me why early detection of these solar storms is critical for us here on Earth?
Absolutely. So the space weather, it affects so much technology, and so when it, early warnings, we're able to mitigate a lot of the impacts from space weather. Early warning allows us to inform power grid operators so they can protect our grid infrastructure and prevent blackouts. Satellites, well, they can be dragged down by solar storms, and it can also increase the risk of collision. So GPS, our farmers today now rely on GPS more than they ever have. Pilots flying around the globe, they also rely on GPS as well. In fact, last year in May of 2024, we had the largest solar storm that we've seen in over 20 years. 20 years ago, our farmers weren't relying on GPS the way that they do today with centimeter accuracy. So we actually realized about $1 billion of economic impact just the corn alone because of that storm.
Thank you so much, Clinton, for joining us, and have a wonderful launch.
Oh, thank you so much. Looking so much forward to it.
Okay, so back to you, Megan and Kelly.
And speaking of launch, 28 minutes until liftoff. Time now for Kelly to answer some of your questions. So we'll take the first one now. This is from Universe Cosmos 4119. What is the most dangerous space weather phenomenon, and how can it affect nearby celestial bodies?
Well, the different phenomena affect things differently, but the most probably dangerous to humans, especially astronauts out in space, is probably those energetic particles. Large doses of energetic particles could, again, cause that radiation sickness, long-term effects such as cancer, or very short-term acute effects such as death very early. So we really do want to make sure that we're protected from those things. There are other dangers, like Clinton actually referred to as satellites. That's the drag or the impact of the space weather on the Earth, and that drags satellites down, and that costs money when satellites don't last as long as they're supposed to.
A wide range of impacts for sure. King Calvin asks, how long will it take for the spacecraft to reach L1, and what happens when they get there?
Oh, it'll take around 6 months for them to get there, or actually 3.5 months. And then once they get there, they're going to spend some time actually turning on all the instruments, making sure that they work properly, that they're getting the data back, and that they understand it. And then it's around 6 months to when we get that science data flowing.
All right. Thank you for those questions. Keep sending them. #AskNASA across our social media platforms. And now, some quick facts about the third mission flying today. NASA's Carruthers Geocorona Observatory is about the size of a small couch and is as heavy as a full-size refrigerator. It will study our planet's exosphere, and studying this outer layer of Earth's atmosphere will help us forecast space weather, understand how atmospheres change over time, and even trace the history of our planet's water.
The goals of the Carruthers Geocorona Observatory are to study the nature and origin of Earth's exosphere and how it evolves over time.
The exosphere itself is the uppermost layer of the Earth's atmosphere. It's comprised almost entirely of atomic hydrogen. This is the lightest chemical species in existence, and it floats away, essentially evaporates off of the top of the atmosphere. And when the sun shines on these atoms, they essentially scatter it off into all directions, and so it glows like a gigantic halo around the Earth. And so that's called the geocorona, that fuzzy halo of light that's given off by those exospheric atoms.
Many times we think of the transition between the atmosphere and space as being this very abrupt boundary where at one altitude you've got atmosphere and the next altitude you have space. But in reality, this transition is much more gradual and can extend over thousands of kilometers. By imaging the geocorona, we can actually answer fundamental questions about the size of the exosphere, the structure of the exosphere, and how it changes over time. And all of this in response to the input from the sun.
And what you're seeing now is a live look at the University of California, Berkeley's Space Sciences Lab Mission Operations Center. This is where Carruthers mission managers are anxiously awaiting liftoff and will monitor the spacecraft throughout its mission.
It's a little early there.
Not yet. They're there. They're taking a little break. We'll take a little break too a little bit, but there they are in that, or will be in that room. Now, but the Carruthers principal investigator is actually here with us. This is Laura Waldrop from the University of Illinois. It's really great to have you here.
My pleasure. Very excited.
So the geocorona, part of the Earth's exosphere that glows, why does it play such a critical role in helping us to understand space weather?
Well, you know, the exosphere plays a vital role in Earth's recovery from these storms. So when they hit, they accelerate ions, and that's how they create these extremely energetic particles that pose the dangers that have been talked about. Well, when those energetic particles collide with an exospheric hydrogen atom, it slows them down. So this weakens those currents, it speeds Earth's recovery. The more hydrogen atoms there are, the faster the recovery. And so what the Carruthers mission will measure is exactly that density, and so we can improve measurements of those recovery timescales.
Great. Yeah, so what are we going to learn about the Earth's history of water through the Carruthers mission?
Oh, so these hydrogen atoms that populate this region were originally liquid water on the surface of Earth. That water evaporated up, became water vapor, and when the sun shines on it, it undergoes a lot of chemical reactions and produces the atomic hydrogen atoms that populate the exosphere. Well, when a drop of water makes it to that altitude as hydrogen gas, eventually it will escape into space. Now, this process is so slow at Earth, but what we don't know is how it might be affected by Earth's magnetic field or by space weather itself. And so by learning more about how it works on Earth, it can also help us understand more about how it happened on ancient Mars, how Mars once lost its own surface water, and potentially help us identify potentially habitable planets beyond our solar system that can retain their water, their surface water, as long as Earth has.
Got it. And the mission was named after American physicist Dr. George Carruthers. Tell us about him.
Absolutely. So Dr. Carruthers recently, as soon as he graduated from the University of Illinois, he invented the camera that took the first pictures of Earth's exosphere. It was deployed by Apollo 16 astronauts on the moon. That's right. And he played such a role in that development. Now, this was a really special camera. It could only take pictures of ultraviolet light, and that's the exact same approach that we're taking to study the exosphere ourselves.
Yeah, so really continuing that legacy. Thank you so much, Laura. I appreciate you being here, and let's see a launch today.
Absolutely. Go Carruthers.
Now, IMAP is the primary mission of the 3 satellites. Cristo Fernandez, who plays Danny Rojas in the show Ted Lasso, has a message for the IMAP team.
Now, I may not be a scientist, as you all might know. I'm more of a football guy. But I do know something about passion and goals. In Ted Lasso, I play Danny Rojas, a joyful and passionate Mexican footballer whose positivity inspires his teammates to remember the pure love of the beautiful game. In the same way, I believe that what you're doing with IMAP is like aiming for the biggest goal of all, understanding our place in the solar system and keeping humanity safe. So from one team player to another, congratulations on this incredible mission. Keep inspiring the world, keep reaching for the stars, and remember, when we play as a team, we can achieve the impossible.
I love that. What powerful words.
That's so important. Teamwork did really make the dream work here. I mean, this is such a team effort, all 3 missions, and so inspirational to hear him send those well wishes. We really appreciate it.
Yeah, and for those who watch the show, I think Krista would admit that the sun is life, and I think Joy's next guest would also agree.
So I'm here with Joe Westlake, who is the Heliophysics division at NASA. Joe, thank you so much for joining me.
Hey, thanks, Joy. Really excited to be here.
Are you excited for the launch?
Oh my gosh, what a beautiful morning that we have this morning, and what a great day to celebrate NASA science and see all of the great work that we're doing here out at Cape Canaveral and Kennedy Space Center.
Yeah, couldn't agree more. So all of the 3 missions today are part of Heliophysics, which is the study of the sun and its effects in space. Can you tell me why it's important to study the sun's influence in space?
Yeah, you think about the sun every day, you see it rise and set. We don't really think too much about how it affects our day-to-day lives. But did you know that it affects everything from our GPS to our crops, to our power systems on the ground, to our commercial aviation, to the satellites and technology that we rely on every day, right? The space weather, the sun, the activity of the sun is something that really impacts our daily technological lives. And these 3 missions are going to provide us information that help us to really live with this star.
And NASA also has a huge fleet of spacecraft that study all aspects of the solar system. How does Heliophysics connect to those other missions?
Yeah, our entire fleet is massive, reaching from the closest to the sun, Parker Solar Probe, to the farthest reaches of the solar system with the Voyagers. But the best connection that we have here is that we are actually connecting the out past the Heliosphere, out into the moon, to Mars, and other locations. We have to know this information to be safe and to bring our astronauts home safely.
Absolutely. And so today's as a rideshare, which is one rocket with 3 missions. Can you quickly just tell me why it's beneficial to be on a rideshare?
Yeah, I think of this as the cosmic carpool, right? We're going to the same location. We're bringing these 3 satellites along together. And with that, we provide immense benefit to the American taxpayer who is paying for 1 launch, and we're bringing 3 satellites along. Really great opportunity.
Thank you so much, Joe, and enjoy the launch.
Thank you, Joy. Really appreciate it.
Thank you. Okay, so now behind us on the Falcon 9 rocket, we're fueling right now. So let's head back to Amanda from SpaceX to get an update.
Thanks, Joy. So quick check of the clock at just under T-minus 18 minutes. The next milestone for the vehicle is coming up in about a minute, which will be the start of Stage 2 LOX loading. So we're about halfway through the propellant load process, and Stage 2 RP1 load is already complete. We're right on track. Now, all 3 payloads today are part of a rideshare mission heading to Lagrange Point 1, or L1 for short. And L1 is unique for a couple of reasons. Spacecraft can remain at this point in a gravitational balance between the Sun and the Earth, and that means that the payloads only need to carry a minimal amount of fuel to remain in control in that region. L1, of course, also offers a clear vantage point to study the sun, space weather, the exosphere, and that capability is critical for the science on board today. Rideshare missions like today's are a great opportunity to cost-effectively launch multiple unique scientific payloads and overall just increase the amount of science that we send to space. The 3 spacecraft aboard, including IMAP, SWIFO L1, and Carruthers, each posed unique mission services challenges. These spacecraft were installed in a 2-tier payload stack configuration. This allows for the safe deployment of each one. The fairing itself also underwent a custom multi-door...
Stage 2 LOX load has started.
I saw confirmation, so Stage 2 is now loading liquid oxygen. The fairing that you can see there on screen underwent a custom multi-door modification, and that enabled post-encapsulation access to IMAP for pre-launch inspections in the hangar. Unique protocols and ground systems preparations were also developed to support the needs of today's mission. For example, each spacecraft required an active gaseous nitrogen, or GN2, purge line up until launch. So 2 new purge supplies were developed for this mission. Historically, only a maximum of 1 purge line has ever been used for pre-launch payload support. So this mission included 3. Also, to support the heightened cleanliness requirements of today's spacecraft, a mission-unique environmental control system was installed, and some of the payloads underwent unique treatments. This included screening and degaussing of both the IMAP and SWIFO L1 payloads to account for their magnetic sensitivities. And finally, on the weather side, in order to enable a spacecraft retest prior to launch, lightning monitoring procedures were developed by the mission teams. So across the board, from installation and integration in the payload fairing to purge and environmental control needs, this mission motivated several service innovations. Now we're well into the propellant load process on Falcon 9 for today's launch. Let's check back in with Megan for more details.
Managing today's launch is NASA's Launch Services Program out of Kennedy Space Center. IMAP, SWIFO L1, and Carruthers will play a critical role in protecting our explorers on the International Space Station and those launching to the moon. Thank you. NASA astronauts Reed Weissman, Victor Glover, and Christina Cook, and Canadian Space Agency astronaut Jeremy Hansen have been busy at Kennedy Space Center, training with ground support teams for their upcoming mission around the moon. The main goal? To make sure everyone's on the same page. Over the past few months, the astronauts suited up, walked out, and traveled the 9-mile journey to Launch Pad 39B. They also spent a lot of time training inside their fully powered Orion spacecraft, going through launch day and simulated flight activities. Get this, it was the first time the crew had ever entered their spacecraft together. And in the case of an unlikely event or emergency at the pad during the countdown to launch, the crew practiced climbing in and out of the emergency egress baskets. Those would carry them from the mobile launcher safely to the ground. All this training helps the Artemis 2 teams plan and understand the timing of events on launch day. That's your Artemis Moon Minute. For more information about NASA's Artemis program, scan the QR code on your screen or visit nasa.gov/Artemis-2. Now, if you're just joining us, we're about 12 minutes away from launching 3 spacecraft to study space weather and how it impacts us. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, NASA's Carruthers Geocorona Observatory, and the National Oceanic and Atmospheric Administration's Space Weather Follow-on Lagrange 1, or SWIFO-L1. Now, IMAP is the primary mission of the 3 today. Now let's take a live look now inside of APL, because IMAP is an international team of about 27 different partner organizations led by Princeton University, but also including APL. That's Johns Hopkins Applied Physics Laboratory there. Great to see people there ready to go.
Yeah, they're anxiously looking at things such as the temperatures and basically the health and wellness of the satellite, making sure it's ready to go, and really anxiously awaiting that acquisition of signal, or that first phone call home once it gets into orbit.
Yeah, APL built the IMAP spacecraft as well as one of its 10 instruments, and after launch, APL is going to operate IMAP. Now, Kelly, we're still getting some great questions from social media, so let's take the next one here. This is Apex Arcane asking, what types of particles are you detecting with these missions?
These are such great questions. Yeah, so
totally.
For these missions, we're detecting everything from UV light, ultraviolet light, which our eyes really can't see very well, in the Carruthers mission, and a little bit in IMAP, to the energetic particles, which is an electron, a proton, as well as other ions such as oxygen and hydrogen and carbon, and that helps us tell things like the electrons are the ones that actually run ahead of the solar storm, and they're very near the speed of light, and they're our warning that something else is coming along. So those are the types of particles that we're measuring with these missions.
Yeah, a lot to take a look at. Thank you so much, Kelly, and thank you again for those questions. Keep sending them along. #AskNASA. Now, IMAP was the first to arrive here in Florida before launch. Its parts were unboxed, then processed at the Astrotech Space Operations Facility near Kennedy Space Center here. In July, SWIFO-L1 and Carruthers both arrived, and then all 3 were configured to fly together. Again, an amazing feat. Finally, last week, everything was encapsulated inside Falcon 9's payload fairing. The 2 halves will protect the satellites during launch. And again, all 3 satellites headed to Lagrange Point 1, a location 1 million miles from the Earth, to study space weather.
From here on Earth, our sun looks steady and unchanging. But close up, it's a dynamic, active place. Loops of superheated plasma follow tangled magnetic fields across the surface, while a steady stream of electrically charged particles, the solar wind, expands into space in all directions. At times, there are bursts of radiation called solar flares, and explosions of plasma and magnetic fields called coronal mass ejections, sending solar storms racing off into space through the solar wind. On Earth, we live in that constant stream of solar wind, protected by Earth's magnetic field. But when the sun suddenly unleashes massive amounts of energy and material, our magnetic field can go haywire during what's called a geomagnetic storm. In May 2024, the biggest geomagnetic storm in over 2 decades hit Earth. The storm spread auroras to unusually low latitudes, disrupted GPS-guided tractors, and forced transatlantic flights to reroute. Storms like these are why NASA and NOAA constantly monitor the sun's activity. NOAA provides real-time monitoring and forecasts of geomagnetic storms and other potentially hazardous space weather events, while NASA's research advances our understanding of the sun's behavior and supports research computer models used by NOAA. Our collaboration is vital to better prepare for space weather. Together, we help protect our technology on Earth, satellites in space, and astronauts as they head to the Moon and Mars.
Kelly, with just 9 minutes away from launch, tell us how much this moment means to you and everyone who worked on all 3 missions.
Right. I am just filled with so much gratitude and so much excitement for the entire team, all the teams that really worked here, here at Kennedy, here at all the different mission teams, as well as SpaceX. We've all just pulled together. People are so excited, and I'm crossing my fingers and toes, hoping for a beautiful launch very soon.
Absolutely. It's absolutely going to be a beautiful launch. Take a look out there, the pad, the clouds, the sunrise in the background. So let us get to liftoff. Let us count down the final minutes to launch with NASA's Daryl Nail and Norman Phelps here in Florida, and Amanda Years with SpaceX in Hawthorne, California.
Yeah, let's do it. We are all ready to go. We're here inside our Mission Director Center at Hangar AE. You can see behind us, this is where all of the management for all 3 spacecraft are located, and it's a high-level area inside there, but they'll be tracking everything that's happening, and so far, so good.
Yeah, so far, so good. I mean, they actually kind of gave a really important call out a little earlier about going to internal power. I really want to highlight the importance of that, right? That means that our spacecraft, everyone, is in their final launch configuration. So similar to, you know, in the morning where you unplug your cell phone from the wall, you detach it from your EGSC there in your wall. That means now that our spacecraft are ready to launch and is ready to do business, just like, you know, your cell phone is attached from his wall, ready to do business with you for the rest of the day.
2 spacecraft on internal power, IMAP and SWIFO. We heard that call out, SWIFO L1. Carruthers, though, not powered up, so there was no switch for them.
Yeah, Carruthers is powered off during launch, so they're not powered on. So obviously there's no call to be on internal power for them. But, you know, this is typical. Some of our launch vehicles launch powered on, some launch powered off, so nothing new to see here.
IMAP is one of the strictest contamination missions that LSP and SpaceX have worked, and we heard a little bit about it from Amanda as we hear that engines are being chilled on the first stage of the rocket. And that is because these are very sensitive instruments.
Correct. And so we're trying to study something that is going to really, literally rewrite the textbooks. We're trying to study how these energetic particles really interact with our solar environment. And so to do that, we need really clean instruments to do that. So think about it like this, right? You're traveling down the road, right? It's a big truck in front of you. It's throwing all this gook in front of on your windshield, right? So I'll call out for RP1 complete there. To actually see where you're going, right, on that road, right, you need to make sure your windshield wipers are clean. So just like we're trying to see what's going on in the local space environment, we need our instruments on all these spacecraft extremely clean. And I want to give a shout out to our contamination teams, both at SpaceX and NASA's Launch Services Program, who made that happen today.
And Amanda, you're out there tracking the countdown from your vantage point in Hawthorne, California.
Yeah, that's right. So as we enter these final minutes before liftoff, weather is still looking good. We have a 10% probability of violation. We heard a couple of key callouts. First, that engine chill has begun on the first stage. That means that we are performing a priming process. So before any propellant flows, the plumbing and engines will be chilled down to prevent thermal shock and boil off when that ultra-cold propellant begins to move at a high flow rate. We also heard that RP1 load has completed for the first stage booster. So that wrapped up the fuel side of the equation, and we are still loading liquid oxygen onto both stages 1 and 2. Now, RP1, rocket-grade kerosene, and liquid oxygen are the primary propellants for Falcon 9. Those are loaded separately onto the vehicle and chilled below 300 degrees below zero. Propellant is intentionally loaded late into the countdown. Colder propellants are denser, and denser propellants mean achieving more performance out of the same tanks. So simply put, the colder it is, the more mass it can move.
Thanks for pressing 4 strong back retract.
That's a great sign that we're on track for an on-time liftoff. So if you look closely, we'll begin to see the process of strong back or TE retraction. Now, at this time, everything is on track. We are working.
We're getting some call-outs from nets that you can't hear. We're listening to. Norman and I are both monitoring, and we're hearing good call-outs so far.
Yeah, so far so good. We are definitely on track for this launch, and you know, go IMAP.
Strong back retract has started.
As you can see there, the clamp arms on the strong back, they will start pulling out. Let's watch that. In the meantime, IMAP has switched off their RF transmitter. They are no longer receiving any data from the IMAP spacecraft. That's intentional. And there go the arms as we see them open up.
NLM, this
We've
is
got
LD
one
on
opening
countdown
up.
1 with status check.
And there goes the other.
this is NLM. NASA's go for launch.
Just heard a great
All right, the
confirmation
SpaceX
there.
launch director checking in with NASA launch manager, Dr. Denton Gibson. He gave the go, another milestone working us closer to a liftoff today.
So like I said before, all the analyses, all the work has come to this moment. So kudos to the team for getting through those polls.
Get ready for, in Joe Westlake's words, our cosmic carpool, taking 3 spacecraft, IMAP, SWIFO L1, and Carruthers on a million-mile journey to L1.
Coming up next in just a few seconds, we're expecting the completion of stage 1 liquid oxygen loading. See those clamp arms.
Stage 1 LOX load is complete.
Great confirmation, right on time. And you can see those clamp arms are free and clear of stage 2. Now, liquid oxygen loading has wrapped up for the first stage, which completes propellant loading for the booster. We mentioned these tanks are also pressurized using helium, and the helium is chilled too so that it stays compatible with the cryogenic plumbing on the vehicle. During flight, that pressurization will help to force propellant into the engines as the tanks empty. And looking ahead a little bit, at the T-minus 60-second mark, Falcon 9 will enter startup. And at that point, the rocket's onboard flight computers will take over. From there on out, the countdown is fully autonomous. Then just inside of T-minus 2 seconds, the 9 Merlin 1D engines will ignite, and once they're at full power, Falcon 9 will lift off the pad and begin its climb to orbit. After engines start, Falcon vehicles are actually held down until all systems are verified as functioning normally before being released for liftoff.
So, Shannon.
Yep.
Stage 2 LOX load is complete.
All right, the stage 2 LOX load is finished. As you can see, as you look at this rocket, you see that burst of LOX coming off the side. They're just clearing out the line there. Nice little clouds formed when that super chilled liquid oxygen hits this warm Florida air. It's a beautiful morning here on the Space Coast. A little past sunrise. They've closed out the gases at the launch pad, as you can see there. The rocket is super cold, so of course it's condensing the moisture in the atmosphere and giving off those clouds. We're getting ready to lock in on terminal count.
That's right, we're approaching the 1-minute mark, at which point Falcon 9 will enter startup.
Falcon 9 is in startup.
Right on time. So at this point, the autonomous flight computers have taken over the launch countdown, and stages 1 and 2 will begin pressurizing for launch. Let's listen in to the launch director's final go.
The launch director is go for launch. T-minus 30 seconds. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engines full power. And liftoff. Go Falcon, go IMAP, go SWIFO L1, and go Carruthers.
And we are flying 3 new missions on a million-mile journey to track space weather. Good looking flight so far. Our tracking cameras getting a great shot as this mission climbs into the sky. We'll be looking now for those engines to throttle down as we go through max Q, the time of maximum dynamic pressure on the vehicle.
Falcon 9 power and telemetry are nominal.
That's right. So coming up is max Q, which is the maximum aerodynamic pressure, largest structural load the vehicle will experience. So slowing it down helps to reduce some of the load it
Falcon 9
experiences.
is supersonic.
And that will help us recover and reuse the first stage. Following max Q, we'll be able to throttle those engines back up as atmospheric density drops.
Max Q.
MVAC chill.
T plus 2 minutes into flight. You can see all 9 Merlin engines. You can at least see the exhaust from 5 of them there. Beautiful shot looking back to the Earth. Got a couple quick call outs coming up. We're going to shut off the engine at 2 minutes and 29 seconds. Stage SEP at 2:32, and then our first burn begins at 2:40. Here we go.
Stage separation confirmed.
And there it goes. On the left side of your screen, you can see the first stage booster falling away now. And on the right side, our second stage, flying IMAP, SWIFO L1, and Carruthers. This first burn is a key burn, Norman.
Correct. This is where we're trying to make sure that we're getting our spacecraft here in their optimal orbit, just to start off with, before we do our transfer into their higher orbit.
Bearing separation confirmed.
There go the fairings, and now you can see all 3 spacecraft revealed.
So now our 3 spacecraft, IMAP, SWIFO L1, and Carruthers, are now exposed to the space environment. So one other note on these fairings, these are new fairings. The SpaceX, of course, is going to attempt to retrieve these fairings once they fall back to Earth. On just read the instructions, that beautiful drone ship that's sitting there in the Atlantic.
And we saw the fairings falling away. I think you can still see, well, that might be some debris, but we got a good shot of them falling. And in fact, as you mentioned, they'll be recovering those, and the booster will be landing on the drone ship. The reason for the drone ship in today's mission is because we need all that performance from the rocket, right?
That's actually correct, yes. So despite the fact that we also were launching due east, right, and taking advantage of the Earth's rotation to give us a little bit more
both
energy.
Both vehicles are following nominal trajectories.
All right, so we heard that both vehicles flying nominal trajectories. That is actually excellent news there. But despite the fact I said before, we're flying due east to take advantage of the Earth's rotation to give us a little bit more velocity here as we got into orbit, so we can carry a little more payload into orbit. We did need all the performance of this vehicle to actually get our payloads to where they needed to go, do all that great science. One more quick call out here on the left there. You see the first stage there. You see the grid fins that are actually deployed. Those are going to actually help guide the first stage back to the drone ship when that drone ship first starts its boost back burn. Excuse me, once the first stage starts its boost back burn, the drone ship's not burning anything.
You may have seen some
but on the
on that
right-hand
first
side of your
too.
screen, we are burning that second stage. Go ahead, Amanda.
Yeah, just noticing here in the great views of that first stage, you may see some soot during the upcoming entry burn and prior to launch as well. So during the entry burn, that will be the second of 3 total burns. Falcon 9 will be decelerating by reigniting 3 of these Merlin engines on the first stage, and that will cause the vehicle to fly through Merlin's exhaust gases, or the rocket's plume. And that's what deposits the layer of soot on the vehicle's surface. It comes from the carbon-based fuel that Falcon 9 uses, and it builds up a little bit more on the outside of the vehicle, which really gives the Falcon first stage fleet the distinctive reused look. So we're looking out for that entry burn coming up shortly. The recovery and reuse of the first stage is what allows us to refly the most expensive parts of the launch vehicle, and that drives down the cost of going to space. When costs are lower, both government and commercial customers can launch more missions, especially in the form of ride shares like today's, and that helps to accelerate research and development. We're looking for that entry burn in just under 20 seconds from now. You'll be able to follow along with the Merlin engines relighting on the first stage with the telemetry on the bottom of your screen.
Stage 1 entry burn startup.
Stage 1 FTS is saved.
And there we heard it. That's the first call. That's the call for the first stage entry burn startup. We're going to be looking for entry shutdown here in a few seconds and finally looking at landing burn shortly thereafter. So stay tuned.
This is the second flight of this booster, and if all goes well, they'll bring it back down and fly it again.
Stage 2 is in terminal guidance.
Just 30 more seconds on that stage 2 burn. And then we'll cut it off and coast for quite a while.
Quite a while until we get to the right point in space to fire it again to put us in our final destination.
Just about 50 minutes or so.
Stage 2 FTS is saved.
All right, so we'll be looking for that cutoff on the right-hand side of your screen.
Stage 1 transonic. MVAC shutdown.
There you heard it, MVAC shutdown.
Cool views on the left with that booster coming back.
Nominal park orbit.
Shoot through those clouds.
That's right, and we're rapidly approaching the landing burn.
It's also got some trailing there.
This landing burn scheduled to start in just a few seconds. There it is, starting up. This will last about 25 seconds, and this will reduce the remaining speed of the vehicle for a soft touchdown on the drone ship. Just read the instructions. The booster is also equipped with 4 landing legs that will deploy for a vertical touchdown, so keep an eye out for that just prior to landing.
Landing leg deploy. Stage 1 landing confirmed.
Beautiful touchdown there of the first stage, and that marks the second landing for this booster.
I must say that never gets old.
No doubt. And now the stack. You can see it's not quite illuminated incredibly well, but up there is IMAP, Carruthers, and SWIFO L1. We will continue to monitor the progress during coast phase, but for now, let's send it back to the host desk with Megan and Kelly.
If you're just joining us, welcome to NASA's live launch coverage of 3 science missions. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, NASA's Carruthers Geocorona Observatory, and the National Oceanic and Atmospheric Administration's Space Weather Follow-On Lagrange 1, or SWIFO L1. I'm NASA's Megan Cruz, and this is NASA heliophysicist Kelly Korrick, who is super excited to see launch today.
So excited to see launch today. It's always a great day to have a launch.
And with the beautiful sunrise we had here, I mean, it was just really fun to watch. And also, there's like a crowd of people here behind us, and we just all heard them cheering and clapping.
Yes, yeah, and the fact that you can feel it here, there is something special about actually being here and being able to feel that. And we're trying to tell you as much as we can about it, but there is something special about feeling the rumble and watching it go up and just knowing all those hopes and dreams and scientific discoveries are on their way now.
Yeah, it was really great to see you guys. Less than 10 minutes ago, again, a SpaceX Falcon 9 rocket lifted off from that launch pad right behind us here, 39A at Kennedy Space Center in Florida. It really was an incredible launch, and you really said it there. It is like we are watching the hopes and dreams of so many people from across the country that have worked together to bring these science missions to launch today.
Yes, and to protect our astronauts and to really understand that space weather that those 3 will study.
Right. Yeah, because all three spacecrafts are going to work together to study space weather. So, Kelly, what is space weather?
So space weather is the effect of the sun on Earth and the entire solar system. That can range for things from creating satellite drag and shortening satellite life to affecting our GPS and affecting our power grids here on Earth. So it's really important to understand it so that we can mitigate those effects.
Yeah, a really wide-ranging swath of effects that we're talking about here. But doesn't NASA and NOAA already study space weather together? Like, what makes these three special?
Yeah, we do study space weather together, and this is the next generation. The SWIFO L1 is very dedicated and optimized to do the space weather that we know today that we need, not that we needed 20, 30 years ago. So that's very specified. And then the next two are the next generation of space weather. What are those things we're going to need when those astronauts are on the moon and Mars? We're learning that through the Carruthers and IMAP mission.
Gotcha. Kelly, thank you so much. Yeah, why don't we break down each one for our viewers right now? So IMAP is the primary mission of the three. It will study the giant invisible shield surrounding the entire solar system called the Heliosphere, which helps make life possible on Earth by protecting us from dangerous cosmic rays. IMAP will simultaneously study the sun's activity near Earth and also create the most detailed map ever of the Heliosphere's boundary.
Yes, that great big boundary, that 9 billion miles away, is our first defense against the space weather that's created by the galaxy and those galactic cosmic rays that can cause some of that radiation sickness we were talking about earlier.
Gotcha. And then there's SWIFO L1, NOAA's newest satellite. It is the first NOAA satellite designed specifically for continuous 24/7 data collection of space weather. And as soon as it measures the strength and speed of incoming solar winds, it alerts NOAA. And this is usually 15 to 60 minutes before solar wind causes geomagnetic storms here on Earth. Those are crucial minutes.
Those are crucial minutes so that we can do those mitigation strategies from power grids to airlines to astronauts.
Yeah. And then there's Carruthers, the first ever dedicated satellite to continuously monitor the geocorona, or the part of the Earth's outermost layer of atmosphere. It actually glows. And this will offer unique insights into how space weather affects our planet. The mission is named after American scientist Dr. George Carruthers, who invented the camera that captured the first ever pictures of Earth's geocorona. Apollo 16 astronauts placed the camera on the moon back in 1972, and it's still there today.
It's still there today, and yes, and we're carrying on his legacy to really understand that part of our Earth's atmosphere that's so important in, again, mitigating those space weather effects.
Gotcha. Kelly, thank you so much. Our broadcast today will take us to around 9 a.m. Eastern Time, when the Falcon 9 second stage will deploy all three satellites into space. Let's welcome back Joy Ung now, who is with Casey Swales, NASA's Deputy Associate Administrator, and Nikki Fox, the Associate Administrator of NASA's Science Mission Directorate.
Casey and Nikki, thank you so much for joining me.
Thank you for having us.
How was launch for you guys?
It was amazing. I have to admit, I completely cried, and I'm trying not to do it again. Even the countdown, I got so emotional on this one. There's so much on there. There's so much heliophysics and so much great NASA science.
And our mom got to be on and got to see it. So it's
fantastic.
amazing. Yeah, it's a beautiful day here at Kennedy.
Absolutely. So NASA is gearing to take astronauts back to the moon with the Artemis missions. Can you tell us how the three new missions today will help get us back to the moon, Casey?
Yeah, absolutely. So, when we go back with Artemis, right, we're going further into space than we've gone in over 50 years. And when we send our astronauts, it's important that we're sending them safely. And in order to do that, we have to understand space weather. So even when you think about packing for a trip, what's the first thing that somebody asks you? What's the weather? What are you packing? And so we have to think about that. Understanding space weather, understanding the sun better, understanding solar flares, solar storms, radiation, how it impacts a spacecraft, how that spacecraft interacts with the crew. That's really important. So we're launching Artemis 2 next year. We're building a sustainable presence on the moon, and then we're going to send astronauts to Mars. And so when we land those astronauts on the moon, land them on Mars, it'll be missions like this that help contribute to making sure they got there safely.
That is very, very exciting. So Nikki, what other NASA science research is happening right now that will help inform the Artemis missions?
There's so much. every mission in our fleet is really playing its part in the Artemis missions. Science enables exploration, exploration enables science. And, we are excited about all of the missions that we have up there. These are going to, really give us cutting edge, the newest measurements. We've been measuring space weather for a long time, but these are just going to be this next generation. And then, of course, a little bit later this year, we'll be launching Escapade, which will go and study basically the weather and the space weather at Mars. And so we really, really are playing our part in the Artemis mission.
And so with astronauts going back to the moon, how will that benefit us here on Earth, Casey?
Yeah, so, Artemis is more than just exploration, right? It's about inspiration. It's about national pride, national leadership. It's about economic growth. For every dollar that's spent at NASA contributes to multiple dollars in economic output. It's about technology advancement, AI, robotics, advanced manufacturing, and that leadership that NASA does, contributes across the world. And so that's really what Artemis is going to bring back to everyone here on Earth when we go.
Thank you so much for joining me, and I'm so glad that we could all be here for launch today.
It was a beautiful launch.
Yes, and thank you for having us.
Go IMAP.
Go IMAP.
Go Carruthers. Go SWIFO.
Go NASA.
Thank you, Falcon.
Okay, so back to you, Megan and Kelly.
Go, 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 go. That's right, guys. All right, we invited you to send in your questions about today's launch. So Kelly is ready for a few more, yeah?
Definitely, yeah. Love the curiosity. Keep them coming.
Yeah, really great questions so far. This one's from Zayshan Ahmed. How long does it take to build and integrate the satellites onto the rocket?
Yeah, these all took a long time. Satellites, 2017 was when this was initially proposed. And so then we took that time to actually build it up. Then you go through a design phase, then a build, then you actually have to test it once you've built everything, and then you're integrated into the spacecraft. So it's taken the time from 2017 to now. So that's around 8 years.
Yeah, and that's IMAP specifically. And then in that process, we identified the rideshare SWIFO L1 and Carruthers, yeah?
Right, definitely, yeah. So within that, then Carruthers was a little bit shorter of a time frame in terms of 21. It was approximately the time when it was turned on and started actually building. But before that, folks have been designing these and thinking about them for quite a while. We always have that next question in mind, and that next generation, always innovating here. So it takes a little while to get those innovations into print and metal and then launched on a beautiful launch like today.
Yeah, that's what's so impressive about scientists, always thinking about the next challenge and how they can meet it. So, okay, well, again, thank you for sending us those questions. Just keep them coming using the hashtag AskNASA across our social media platforms. All right, so the IMAP spacecraft was built by Johns Hopkins Applied Physics Laboratory in Maryland. Here with us now is Dr. Martina Goulidou, a project scientist with APL. It is so great to have you here, Martina.
So happy to be here. I think my heart is still racing.
I know. How was it to see launch today?
Oh, it was amazing. I teared up a little bit.
No, I'm glad. Again, this is so important to you guys. Again, she's part of the IMAP team. Yes. So really, we've been talking about the science behind what we're trying to study here with these spacecraft, describing the heliosphere as a bubble, right?
Yes, exactly. You can think of the heliosphere as a bubble that is being inflated by the solar wind, a constant stream of charged particles that is being emitted by the sun. Mm-hmm. So maybe we can pretend this little guy is our sun.
Yes, so Martina had homework for me. She asked me to bring some props. So I have a balloon and I have a balloon pump. So you're saying the pump is going to be like the
Yes, the sun. And the solar wind. So the stronger the solar wind, the more the heliosphere is being inflated. Mm-hmm. And now when the solar wind gets weak, our heliosphere is being deflated.
Okay, so the pressure inside affects the shape, the size.
Exactly.
Yeah, so what about the outside, though? What is that expanding into?
Yeah, so the whole heliosphere is actually flying through our galaxy and what we call our interstellar medium, gas and dust that is existing between the stars. When the pressure from that medium is strong, the heliosphere contracts even more.
Even more, okay.
And when the pressure of that medium is weak, it allows the heliosphere to breathe again and expand.
So
there we
like
go.
This. Yeah. So basically, we are taking into account internal and exterior forces that changes the shape of the heliosphere. But why is that important to know?
Yes, so our heliosphere is actually a shield that protects us from harsh galactic radiation. So we don't know whether life would exist at Earth the way it is now if we didn't have that protective bubble, right? So it is important as we go and explore other exoplanets in other astrospheres, we want to understand first our home in the galaxy and how we came about.
And that's what IMAP's going to help us study.
Exactly. Go IMAP.
Go, that's right. Go IMAP. Thank you so much, Martina. I appreciate you being here. And congratulations. Congratulations. Okay, so IMAP is going to start collecting data about 3.5 months after launch. For more on that, let's bring back Joy, who's now with Dave McComas, IMAP's principal investigator from Princeton University.
Dave, thank you so much for joining me today. How was launch for you?
Oh, it was so exciting. We are all so happy. The whole IMAP team is just delighted.
So IMAP, as Megan said, is going to reach Lagrange Point 1, which is 1 million miles from Earth, around January. What do you expect IMAP to be doing and seeing as it takes measurements in January?
Yeah, so just incredible science. We'll be measuring the sun, what comes out from the sun, the particles, the magnetic fields. We'll be doing incredible space weather, helping our whole country understand what's happening that's coming towards us from the sun. And we'll be looking at the outer part of the heliosphere, the boundary of our solar system, basically, and how that interfaces with the galactic medium around us.
As you just mentioned, IMAP is going to be studying the edge of the solar system, the heliosphere, as well as real-time solar activity coming off of the surface of the sun. Why was it important to build a mission that could do both of those things?
So we've worked at both of those pieces before with other missions, but they've been on different spacecraft. They haven't been intercalibrated. They haven't been able to do the holistic science. Putting it all together on one spacecraft allows us to do the complete integrated science and understand our neighborhood of the sun.
And so as the principal investigator of IMAP, what are you most excited for discovering with the mission?
What I'm most excited about is the things I don't know about. I know we're going to do a lot of great science, all the stuff we promised in our proposal, great new measurements, great new understanding. But the really exciting thing is when you fly new instruments that are much better than older instruments, you discover new things that you can't even imagine when you launch the spacecraft. That's really exciting.
And how do you anticipate IMAP to be working with all the other heliophysics missions that NASA has?
Yeah, I think IMAP will be sort of a cornerstone for all of the heliospheric missions. There's a lot of great science that can be done by comparing data from different missions in different positions, and we hope to be sort of in the lead of doing that work.
Well, thank you so much for joining me, and I'm so thrilled that IMAP launched today.
We are too. Thank you so much.
Okay, and so let's head back to Megan and Kelly.
Managing today's launch is NASA's Launch Services Program based here at Kennedy Space Center. It essentially acts as a broker to match uncrewed spacecraft like the 3 today with suitable rockets for launch. NASA's Daryl Nail spoke to a flight and structural loads analyst about the challenges of getting 3 spacecraft safely into orbit.
And we are here with Natalie Hintz, who actually did the structural loads analysis for the IMAP mission. Thank you for being here.
Yeah, thank you for having me.
So structural loads sounds complicated, but explain why it's important for us to know what's going on inside that rocket with regards to all the structures.
So we have this spacecraft which has all of these delicate instruments and components that have been designed with their science in mind. However, they're not really that structurally strong, and we are taking these spacecraft, we're putting them on top of a launch vehicle, in this case a Falcon 9, which has all of these rocket engines that are going to blast it from the surface of the Earth into orbit, and it's going to endure a very violent launch environment.
It's a lot of shake, rattle, and roll happening inside of a rocket.
Absolutely. So when it comes to a spacecraft and a launch vehicle system, it's going to be much more complex. Imagine that the central beam is a launch vehicle, in this case a Falcon 9, and we have a mass at the top which is representing a spacecraft, in this case IMAP. Look at how that system is being excited. I'm not shaking the base very much here, and yet look at how much it is actually vibrating. I'm activating the first mode of the system.
So we think of this as, something that's not good inside of a rocket if it were to move around like that in that clamshell.
We actually have a system of spacecraft. So we have IMAP, and we also have its ride shares, SWIFO L1 and Carruthers, which are hanging out on an ESPA ring just underneath IMAP.
That's right.
So I actually brought my own SWIFO L1 and Carruthers here so that we can understand how that's going to change the system.
These are wood blocks, but they got weight on them, and so they essentially kind of, they're a good analog for what you're doing, right?
Exactly. So we can attach them here to this rideshare ring, and that is going to simulate the addition of the mass and overall structure of those rideshare spacecraft. All right, so you can already see here the static deflection is changing because we've added mass to the system. But not only that, we're not really interested in the static shape here. We are interested in the dynamic shape. So again, it's sitting on the pad, getting ready for liftoff. The engines ignite, and look at how much more it is moving. Not only that, but the shape that it's moving at has changed. So looking at the spacecraft here, we have IMAP on top of a payload adapter and a rideshare ring, which has SWIFO opposed to Carruthers. And all three of these spacecraft are forming one unique payload stack, one unique system. Throughout our coupled loads analyses, we derived the launch environment that these would experience during flight. And much like I shook this rocket model, we also shook those spacecraft during vibration testing to make sure that they are rated to and can survive the vibrations that these spacecraft will see during launch. So in the end, we found that through analysis and testing, these three spacecraft are ready to go and they are good for launch.
Thank you so much, Natalie. Appreciate the time, and thanks for explaining it.
Absolutely.
Now, this isn't the first time NASA and SpaceX are working together to send great science into orbit. For more on that, let's head back to Amanda in Hawthorne.
Thanks, Megan. Since 2016, NASA's Launch Services Program has partnered with SpaceX to fly some of the agency's most important science missions, spanning everything from Earth climate monitoring to astrophysics and planetary defense. In 2016, we launched our first LSP mission, Jason-3, which was a payload to measure global sea level rise. That success paved the way for TESS in 2018, a mission that transformed our search for planets by scanning nearly the entire sky for new worlds. In 2020, Sentinel-6 Michael Freilich carried a radar altimetry reference mission to extend the legacy of sea surface height measurements. This is critical to understanding climate change. Altimetry is the study of height, or measuring altitude, things that go up. And in this context, Sentinel-6 carries a suite of instruments which provide high-accuracy altimetry data monitoring for sea surface height, significant wave height, and wind speed, as well as monitoring inland water levels and ice characteristics. Then in 2021, LSP entrusted Falcon 9 with DART, the first ever test of planetary defense. And that went on to prove that humanity could intentionally change the orbit of an asteroid moonlet. That same year, IXPE opened a brand new window to the universe by measuring the polarization of X-rays from black holes and neutron stars. The collaboration continued with SWOT in 2022, which is now delivering detailed global maps of rivers, lakes, and ocean currents. And then with Psyche in 2023, a Discovery-class mission to explore the metal-rich asteroid 16 Psyche. This will reveal how planets may have formed, and that launched on Falcon Heavy. PACE, GOES-U, and Europa Clipper all launched in 2024. Europa Clipper, NASA's flagship mission to Jupiter's moon Europa, was sent to search for signs of life beneath its icy shell. PACE and GOES-U are working to advance our understanding of plankton, aerosols, clouds, and ecosystems that regulate Earth's climate to strengthen severe storm and space weather monitoring, respectively. In March of this year, Falcon 9 launched the SphereX mission to survey the entire sky with infrared light. That launched alongside Punch, which will study the sun's outer atmosphere. Just in July, Tracers delivered twin satellites to investigate magnetic reconnection, the fundamental driver of space weather. That brings us to today, where IMAP will head out to chart the boundary where solar wind meets interstellar space. And later this year, Sentinel-6B will take the next step in precision ocean altimetry, extending the global sea level record, which is critical for tracking climate change. Now, looking ahead, the Nancy Grace Roman Telescope, an observatory designed to study dark energy and dark matter, search for exoplanets and image them, and more, will tackle some of the biggest questions in science while generating data to help protect the Earth. In less than a decade, SpaceX has built a proven track record with NASA's Launch Services Program, establishing Falcon as a dependable launch platform for some of the most ambitious and groundbreaking science of our time. And that brings us back to today's IMAP mission, where we are just under an hour from the beginning of spacecraft deployment. So let's check back in with Megan.
Yeah, it's time for more questions from social media. The first one is, what new technology is being used on these missions?
That's a great question. So a lot of these missions have developed new technology in terms of the cameras that they use, in terms that like the camera in Carruthers. Although Dr. George Carruthers built an amazing thing. There's been a couple of advancements since 1972.
I would hope so. Yes.
Yes, I hope so. So there's been some updates there. All of the detectors have been updated, and all the new instruments on IMAP are improvements upon the older versions of these. And for SWIFO L1, since it's operational, it is an upgraded version of former instruments, but it's not too far off because, again, we want to make sure that they're the same, we have a consistency in those measurements and that they're very similar to past measurements.
Yeah, absolutely. That makes sense. You want to make sure you're still, even though there's advancements like comparing apples to apples,
exactly.
essentially.
Yeah, you want to keep that the same.
Got it. Same fruit. Now, this next question is Chili Maple. How long will mapping the Heliosphere take, and when will the research contribute to safeguarding Earth?
Oh, that's a great question.
Yeah.
So to actually map the Heliosphere, it's going to take a while because the spacecraft takes turns and basically gets little bits of the sky every time it turns. And to make that full rotation as it rotates with the Earth, it takes about a full year to get one of those maps. So that's great because we have a 2-year mission. However, it also has the iAlert system on IMAP, which will be able to feed us data basically instantaneously or within 30 minutes, get data about space weather that will be beamed back. So that long-term space weather, that galactic space weather, will take about that year, but that instantaneous will get started in 6 months once it's fully commissioned.
Wow, very impressive. Thank you so much, Kelly.
Yeah.
And as Kelly said, really, really great questions. Yeah, keep them coming. You still have time. Again, using that hashtag AskNASA on our social media platforms. Now, all three spacecrafts, IMAPs, Carruthers, and SWIFO L1, will monitor space weather from Lagrange Point 1. That's about 1 million miles away from Earth towards the sun. And specifically, as you can see in that graphic, they're specifically on the line connecting the two. Why specifically here, Kelly?
Specifically there at the L1 point is the balance between the gravitational pull back to Earth and the gravitational pull towards the sun that allows them to have that use relatively little fuel and stay there for a while. It also gives them the direct view. If you're around Earth, sometimes Earth gets in the way of the sun view, sometimes the moon gets in the way, and so you don't have those continuous viewing angles. So you really want to be on that line to save fuel and to have the direct view to the sun and to be in front of the Earth so that we have those 30 to 60 minute warnings.
Yeah, and again, I love that this is a rideshare mission. You know, we identified 3 that were going to want to go there anyway. They might as well fly together.
Right, definitely. It's again, the cosmic carpool is the best way to put it. It was the trains going in one direction, everybody get on, let's stop there.
That's amazing. Now, all 3 satellites will continue the important work of space weather satellites already at Lagrange Point 1, but that have been operating well beyond their intended lifespans. We were kind of talking about that a little bit ago because of one of the social questions. You know, SOHO launched in 1995 and was only supposed to run for 3 years, but it continues to collect data. Then ACE launched in 1997 and, like SOHO, far exceeding its 5-year lifespan. And then there's Discover, which was also designed to operate for 5 years, and yet that launched 10 years ago, Kelly.
Yes, all of these spacecraft have been doing an amazing job at understanding our space weather and started as really more science-driven, that inquiry. And so we learned so much about space weather from the 1990s to now. And so we need really that upgrade, that next generation. What really works for us? What do we really need to know? Maybe a quicker cadence or a little less cadence to really get the information down to protect everything from our astronauts to our pilots and our farmers.
Yeah, and what I find really impressive again is NASA and NOAA have been monitoring and studying space weather together for more than 50 years. So let's go back to Joy, actually. Now she's with Paul DeBar, Deputy Secretary of Commerce.
Paul, thank you so much for joining me.
Oh, it's great to be here. Great to be back again for another launch.
How was that spectacular launch for you?
I mean, it was perfect. I mean, what a beautiful day, and most importantly, all the scientists and engineers who've been working on all 3 missions for a very long period of time. This is a culmination of a lot of science and effort.
Absolutely. So can you tell me, how do NASA and NOAA work together when looking at space weather?
So overall with space, NOAA has a giant set of constellations of satellites looking at all sorts of different weather in LEO and GEO and obviously dealing with hurricanes. But when it comes to space weather, obviously it's a much bigger, newer issue with technology in space and telecommunications and 5G and 6G coming up and GPS. For us to be able to move from science of taking a look at heliophysics to being able to see what it could affect our technology and be able to react to that is very, very important, and that's what this mission's about.
And how has studying space weather for the past 50 years benefited us here on Earth?
So the basic discovery of heliophysics, which some of the other missions, IMAP in particular, is doing right now, has laid the groundwork for us to understand the various heliophysics issues and magnetic storms, coming off of the sun, and has allowed us to be able to build a sensing device for what's called applied applications, right, for applied issues, and that's what our satellite is that's on this package here today.
Have there been any memorable predictions that have helped mitigate the effects of space weather on Earth?
Yes. So in May 2024, so not that long ago, there was about a 3-day storm period in the sun. And we had existing assets to be able to map that. And we were able to support giving notifications, just like we do with hurricanes at NOAA, but for, in this case, a space storm, coming from the sun. And we were able to help, various different technologies and users to take precautions. It still caused impact on Earth, and so that's why having a next generation and our efforts in Boulder for our Space Weather Center of communicating this data that we will be getting to a broader number of people around the world will be able to help move that forward and prevent issues from solar storms.
Yes, it's definitely a very exciting time for forecast and for science. So thank you, Paul, so much for joining me.
Thank you.
And I'm so glad that we had a wonderful launch together.
Thank you very much.
Okay, so let's head back to Megan and Kelly.
Thank you both. All right, it's been about 40 minutes since launch here at Kennedy Space Center. Let's check back in on IMAP, SWIFO L1, and Carruthers with Daryl and Norman.
All right, we're coasting and doing a good job of coasting as we continue to climb into this trajectory. We are going higher and higher and higher. This is a very highly elliptical orbit that we're going into, much different than just your circularized orbit for low Earth. We got to get out to 1 million miles, so we're really getting high in this orbit.
Yeah, correct. So for us to go to L1, it's almost as if we have to do an escape trajectory, although not quite. Our C3 is still kind of negative, so we're not quite on
our C3.
Our C3, yeah, it's the energy it takes for us to actually leave Earth's gravity, right? So it's not quite positive, which means we would need that to actually be, to actually leave Earth's gravity field. But we're close, right? So we need that highly elliptical orbit for us to actually achieve that. The other thing I'll mention, too, is that, you say we're coasting. People are like, oh, you're not doing any work right now. Well, that's not true. We're actually right now doing a very optimized flight right now. We're trying to make sure that we fire our second stage at just the right time so that we can transfer from our trajectory or our altitude we're at now to the higher trajectory that will push us at the point where we actually can separate our spacecraft so that our spacecraft can go to where it needs to go to do its science.
For the record, I'm still working, and and you are too.
Still working, yeah.
Yeah, still working, but coasting. And thank you for pointing that out. We also will be sun-facing.
Correct.
And that's important at the time of release.
Correct. So the idea there for sun-facing was that we wanted the sun right to be on the solar panels for IMAP, and that's for a couple of reasons. As you have heard before, IMAP's on internal power, right? So for us to get back some of that juice into our batteries, we want to be sun-facing so all that sun's energy can get back into our batteries, right? Solar panels produce energy, which is always a great thing for our spacecraft. We like that. Yeah. The other thing there, too, is that by actually using the solar panels on IMAP, we actually are using almost as a solar shield, right? So it's reducing the thermal strain on the instrument suite of IMAP and the instruments on both Carruthers and SWIFO L1. So they're actually doing double duty there. So we want to thank IMAP for their service to the cause here.
Absolutely. And in fact, because of that shading, Carruthers needed their own warmth, right? Some heaters in order to keep them warm because they can't see the sun at the moment.
Correct. And there was a fear at some point that given that Carruthers was not on, that the hydrazine lines that they had, the rocket fuel would possibly freeze. Freezing lines is bad.
Especially when it's your fuel, yeah.
Exactly. So we want that to be liquid coming out. So we want to make sure we had heaters on those lines provided by SpaceX to actually make sure that did not happen.
All right. Well, the next time you see us, we'll be getting ready to do a second burn of that second stage, which will be key to get it into and set it up for the separation of all 3 spacecraft. So we hope that you'll join us then. That's in about T plus 1 hour and 12 minutes, so just a little over a half hour. In the meantime, we'll send it back to Megan and Kelly.
Yes, Megan and Kelly both here, and
Yes.
and
And in it for the long haul.
and
yes.
in it for the long haul because, yes, as they just said, the second stage is going to coast now for about another half hour. So it's time for this team to take a little break. But again, we will be back 8:40 a.m. Eastern Time to continue with live coverage of IMAP's Swiffle L1's and Carruthers' journey to Lagrange Point 1.
Yep, join us for that separation. That'd be great.
Exactly. 8:40, set an alarm. See you then. I'm NASA's Megan Cruz, and this is NASA heliophysicist Kelly Corrick.
Hi, everyone.
We are back from a short break to continue live coverage of 3 new space weather missions that are headed about 1 million miles from Earth. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, NASA's Carruthers Geocorona Observatory, and the National Oceanic and Atmospheric Administration's Space Weather Follow-on Lagrange 1, or we like to lovingly shortly call it
SWIFOL1.
Now, liftoff was a little more than an hour ago at 7:30 a.m. Eastern Time. If you missed it, check it out now.